Bismillah ar-Rahman ar-Rahim. Today we are going to talk about signed numbers, okay? So far we have only talked about, or we dealt with unsigned numbers, unsigned binary numbers. So to represent signed integers in binary, we have to do two things, basically. One is to fix the width of the number. We have to pick a width like 4-bit, 3-bit, 10-bit, 64-bit, whatever, okay? You have to deal with that width. You cannot exceed that width, okay? The second thing is to embed your sign of the number, or the sign of the number, embed it in the number itself. And the way we do it, there are three ways to represent negative integers, okay, or integers, signed integers in general, okay? The first way is sign and magnitude, or signed magnitude, okay? Representation, okay, so three representations basically, sign and magnitude, and the second one is the one's complement representation, and the third one is the two's complement representation. Okay, this is please pay attention to this part here, this information here, before we get started with these representations, because it will give you a piece of information that will help you understand half of the problems in this section of the course. So for all the three representations, regardless of the representation that you use, okay, for all the three representations, the sign bit is going to be placed in the most significant bit, okay? So if you have, for example, if you have 4-bit number, then the sign bit will be bit number 3, okay? Start with bit number 0, 1, 2, and then 3 is the sign bit. If the sign bit is 0, we know that the number is negative. And if the sign bit is 1, then if the sign bit is 0, then we know that the number is positive. And if the sign bit is 1, then we know that the number is negative, okay? So this is regardless of the representation, okay? Regardless of which representation we use. You just examine the sign bit, okay, which is at the most significant bit, and you immediately know that the number is positive or negative, okay? The second information, the second fact that is also applicable to all the representations, okay, is that positive number, the decimal value of a positive number is the same regardless of the representation. It is going to be equivalent to the conversion of that binary number to decimal number, okay? So the positive for the representation of positive numbers is invariant with respect to the representation, okay? So whatever representation that you use, positive numbers are going to be the same for all. The only difference is in representing negative numbers. So for positive numbers, you are going to get the same bits for all the representation. However, for negative numbers, each representation will store negative numbers in a different way. Okay? Got it? Okay, so let's take an example to test your understanding now. Suppose that we use 4-bit to represent signed integers. Okay? What is the decimal value of the following signed integers? What is 0, 1, 1, 0 if it is represented in 2's complement? Who can answer this question? Just from the information that I gave you before. As I told you, is this number positive or negative, first of all?
It's positive.
It's positive. Why? Because the sign bit is 0. Okay? So, as I told you, how to get the value, the decimal value of a positive number? You just convert it to decimal. As simple as that. You use the algorithm that we learned before. Okay, so what is the value of this number?
6.
It's 6. So the decimal value of this signed number is going to be plus 6. You must put the plus, okay, to indicate that you know that this number is signed, okay? Okay, what if I say to you if the same number but represented in one's complement? What is the decimal value?
Decimal value 6.
It is the same, right?
Yes.
Going to be the same because positive for positive numbers, we have the same representation in all the representation, in all the three representation. Okay, the same number, the same bits in all the representations. So, okay, for the same bits in sign and magnitude, okay, we get also a plus 6 as well. This is just to confirm your understanding of this fact. So in all, I'm going to read it aloud and please pay attention. In all the three representations, if the integer is positive, then its value in decimal can be obtained by converting the binary to decimal. That's it. Okay, regardless of the representation. And where do we get the sign bit from? The most significant bit in all the representations. If the sign bit is 0, then we know the number is positive. And if the number is positive, its value is going to be the conversion of its binary form to decimal form. That's it. Okay? So in conclusion, only negative numbers need special handling to obtain their value in decimal. And this differs from or for each representation. So for that, we need to discuss each representation by itself. Now we start with the signed magnitude representation, okay? So this representation is the one we use to represent signed decimal integers, okay? Like, for example, you say, well, plus 15. This is the sign, and this is the magnitude. Negative 71. So this is the sign, and this is the magnitude. Okay, the sign is negative, and the magnitude is 71. Okay, plus 108. The sign is plus, and the magnitude is 108. For binary integers, we use the most significant bit for the sign bit. This is a repetition of what you already know. Okay, so if the sign bit, if the most significant bit is 0, it is positive. If the most significant bit is 1, the number is. If the most significant bit is 0, the number is positive. If the most significant bit is 1, the number is negative. Okay? And the remaining bits represent the magnitude of the number. Okay? So let's take an example. Okay? So using 5-bit signed integers using sign and magnitude, and I'm abbreviating it here as SM representation. What is the decimal value of the followings? Okay, we have this number here. What is the decimal value of this number? Come on, guys.
Positive 13.
Yeah, it's plus 13 because this is positive. Okay, so its value is just the conversion of this number to decimal, and you put a positive here. And this number again, it's positive, so I can do this for you. It's positive 14. Okay, what about this one? I'm going to leave the tough ones for you. Okay, this one is negative number, right? So what is it? What is the value here?
Negative 3.
Negative 3.
Negative 3. Excellent. Okay, so we first of all we just write the sign, which is negative, and then we convert the remaining bits to decimal. Okay, which is 3. What about this one?
Negative 5.
Excellent. Yeah, negative 5. You get the hang of it now. Okay. Now, what are the advantages of sign and magnitude? Basically, we are familiar with it. Okay, and it is easy to find the negative of a number. If you want to find the negative of this number, for example, Okay, all you have to do is to flip this bit. Okay, the sign bit. Okay, it's exactly the same as flipping the sign of this bit. Okay, this number here, for example, minus 71. What is the negative of this number? It's plus 71, right? So eventually, in the binary world, okay, we have a sign and we have a magnitude. Okay, all we have to do is to invert the sign. Okay, if the sign is 1, we put it to 0. If the sign is 0, we put it to 1. Okay, so it is easy to find the negative of a number. Okay, so what is the negative value of 1011? It is going to be, we just flip this bit and then keep the rest of them the same. So this is going to be a plus 3. So this must have been a minus 3. Okay. Okay. What are the disadvantages? Disadvantages is that you have 2 representation of the 0. We realize that, right? We have a plus 0 and a negative 0. Plus 0, for example, in the case of 4-bit, okay? In the case of 4-bit, we have 0, 0, 0, 0. This is plus 0, right? And what is the negative counterpart of plus 0? It's 1, what? 0, 0, 0, right? This is negative 0. Do you see that?
Yes.
Okay, so this is bad. Okay, this is terrible and bad. Okay, terrible and bad. Because why? Because you are wasting the range by duplicating a number. Okay, by duplicating the representation of the same number twice. Okay, I mean once, duplicating it once, of course. Okay, so we have plus 0 and negative. We have 0. Why do we need to have minus 0? We don't have. We don't need. We could have used this to represent another number. Okay, to increase our range. Okay. The other disadvantage is that we have to use different circuits for addition and subtraction. Okay. What about the range of the representation, the sign and magnitude representation? If you use an n-bit sign and magnitude representation, then this gives us a max of plus 2 to the n minus 1 minus 1, and the minimum of negative this exact number. Okay, the negative of this maximum. Okay, so who can tell me where do we get this from? This number here. Use your information in chapter 1. What is the maximum? What is the maximum? So you have an n-bit sign and magnitude. Okay. What is the maximum number that you can represent? It must be positive first of all. Okay, and then the remaining bit must be what? In order to maximize your number, the remaining bit must be zeros.
Ones.
Yeah, they must be ones, all ones. So how many of them do we have? N minus 1, because the number is n bit. We have n minus 1 ones. So what is the value of this number in decimal? This is basically it is equivalent to, okay, when we say, if we use the unsigned realm, okay, unsigned world, okay, it is equivalent to 1 0 0 0 zeros, okay, n minus 1 zeros, okay, and then minus 1, right, in binary. Yeah, we get that. So what is this now? It's 2 to the n minus 1. So it's 1 followed by n minus 1 zeros, right? minus 1. That's the thing that we get. It's plus 2 to the n minus 1 minus 1. And the negative counterpart will be the minimum. What is the negative counterpart? It's 1 followed by all ones. I have n minus 1 of them. Okay? And this is exactly going to be negative 2 to the n minus 1 minus 1. Okay? You get that? Okay, let's take an example of this. Okay, using 4-bit sign and magnitude, what are the minimum and maximum in binary and decimal? Okay, in binary, the minimum is going to be all ones. Okay, and the maximum is going to be 0 followed by all ones. Okay, and that using the formula here, okay, is 2 to the 3 minus 1 with a negative sign, okay, which is minus 7. And then the positive here, the positive counterpart is going to be 2 to the 3 minus 1 with a positive sign, okay? Clear? Is it clear? Any question here? Please don't fall asleep, guys, okay? Pay attention. This lecture is really important, and it will play an important role in your midterm exam, okay? All right. So now we discuss the ones complement, okay, representation. Let's continue that, it's representation. Okay. And the thing that we need to worry about now is to find the decimal value for a negative number in one's complement. Okay, how to do that? Basically, we complement all the bits. We complement all the bits and then convert the decimal. Okay, let me test your understanding again, because although I'm afraid that you will not answer. What about if you want to find the decimal value of a positive number for one's complement?
You just do it normally because
Excellent.
it's positive.
Yes, excellent. Yes. So for positive numbers, as I told you, it doesn't depend on the representation. It's all the same. Okay, all representations represent positive number in the same way. All right, which is the normal way we use. All right. I mean the way we use to, which is the unsigned way. Okay. Except that it has a 0 in the leftmost bit. Okay. So now using 7-bit ones complement representation, we would like to find the decimal value of this number here. Okay, again, just to confirm your understanding, what is the value of this number? This is going to be, it's positive, so you just need to convert it to decimal, right? So this is going to be 13 plus 32, which is 60, what?
61.
Hold on, 13 plus 32, 54, okay? So it is a plus 45, I'm sorry, 45, not 54, okay? Plus 45, okay? So it's just a matter of, this is unit or chapter 1 material, okay, or unit 1 material. It's a matter of converting to a decimal, okay? Converting a binary to decimal, and then just the sign is inferred from the sign bit, okay? You must put the sign, otherwise you'll lose credits, okay? If you don't put the sign, then the number is unsigned, okay? Even if it is positive, you must put a sign, okay? Now for this number, you must, if you have paid attention here to what we do, okay, so we simply complement all the bits and then convert to decimal, okay, if it is negative. So this is negative now. So what do? We complement all the bits first. So this is going to be 0, 1, 0, 0, 0, 0, and then 1, right? And then convert to decimal. What is the decimal value of this? it's going to be 1 plus 32, which is 33. Okay, 33. However, the sign of this number is negative. Okay, so this is minus 33. I'm talking about this number is negative 33, but this number is positive 33. Okay, you get that? Any question? Okay. Now I'm going to introduce a terminology here. Okay, so the terminology is to differentiate between what we call ones complement representation as a representation of signed numbers, and to say the ones complement of A, for example, a number A. Okay, if you take the ones complement of A, and it's nothing but a complement, the bitwise complement of A. Okay, so using 7-bit ones complement representation, find the ones complement of this number. Okay, of, let's say, A. Okay, so here my A is this number here, and to find the ones complement of A, the ones complement of A is the negative counterpart of A. Okay, so the negative counterpart of A is a complement, nothing but a complement in the ones complement representation. So in my case here, my negative A is going to be what? Just take the complement of all the bits. Okay, so this is this. If the value of A is what? The value of A is itself A without complementing it. The value of A is 7 plus 16, which is 23. Okay, plus 32, which is 23 plus 55. So A is plus 55. Okay, so we must infer from this that negative A is in decimal is minus 55. Okay, so this one here is minus 55 in one's complement. Okay, let me ask you this question. What is minus 55 if I use 7-bit representation of sign and magnitude? What is minus 55 in sign and magnitude representation? In sign and magnitude, all you have to do is to complement the sign bit, right? So in sign and magnitude, you have to complement the sign bit and leave everything as is. So this is equal to minus 55. Okay, all right. But in one's complement, the minus 55 is represented in this form, which is the complement of all the bits, not just the sign bit. Okay, so notice the difference here. This is minus 55. This is minus 55 in sign and magnitude, and this is minus 55 in one's complement. They have different bits. Okay, but the positive numbers, okay, are the same regardless of the representation. Okay, is this clear?
Clear, yes.
Okay, cool. Let me just remove the stuff that we don't need so that you don't get confused. Okay, I'm sure that I'm going to get a question about this later. Okay, but right now let's assume that everything is clear. Okay, so the one's complement representation also suffers from +0 and -0. Okay, so if we say 4-bit one's complement representation, What is plus 0? It's going to be a 0, 0, 0, 0. That's a plus 0, right? What is negative 0 in one's complement?
One, 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 one.
1, 1, 1, 1.
Excellent. Yeah, you just complement all the bits. Okay, so this is plus 0, and this is negative 0, which is bad. Okay, it's not a good thing. Okay, so it's not perfect. So that's why it's not used among other reasons as well for arithmetic. Okay, we use 2's complement, as we will see next. Okay, what about the range of numbers? It's going to be the same as the positive, as the sign of magnitude range. Okay, for the positive numbers, okay, the maximum that we can reach is 0, and then followed by all ones, and this is 2 to the n minus 1, okay, and that's a positive number. Now the negative of this is going to be the lowest number, right, which is this number here, and its value is going to be the negative of this, exactly. Okay. Okay. Any question? Let me move on to 2's complement if there are no questions. 2's complement is the best representation, okay? And it is the one that is used in digital systems nowadays, okay? And to obtain the decimal value of a negative integer represented in 2's complement, we first find its one's complement, which is basically the complement of all the bits, okay? And then we add 1 to it. Once we do that, we convert to decimal, and then we get the value of the negative number. Okay, and for positive integers, you know that it's no difference than the other two representations. It's going to be the same. Okay, so for positive integers, you just need to convert to decimal and then put a plus sign in front of the number. And how do we know the positive from negative numbers? By inspecting the most significant bit. Okay, let's take an example. 6-bit 2's complement representation. Find the decimal value of this number. Yeah. What is the value of this number in decimal? It's, who can tell me?
We first add 1, then flip all the bits.
I just want to find the value of this number, right? First of all, let me ask you this. Is the number positive or negative?
It's positive.
Okay, so for positive numbers, what do we do? Regardless of the representation, what do we do with positive numbers? We just convert them directly to decimal. That's it, okay? Regardless of the representation, okay? So if you find out that the number is positive, it doesn't need a special treatment. You just convert it to decimal and put a plus sign in front of it. That's the value of the number, okay? So this number is nothing but 10 plus 16, which is plus 26, okay? Yeah? What about this number? Now we're talking. This is a negative number, so now what you said apply. Okay, you take, first of all, you take the complement of this number. The complement is going to be the one's complement, okay? One's complement is going to be 0, 1, 0, 0, and then 1, 0, okay? And then you add 1 to that. It's going to be 1, 1, 0, 0, 1, 0. Okay, so now I convert this number to decimal, and then for the value of this number, it's going to be the magnitude of this number, but I put a negative sign because this number is negative. Okay, so what is the value of this number? It's going to be 3 plus 16, which is 19. Okay, and then this number is negative. I know that this is the value of this number. Okay, you get that? Any question? Let me take another example. So 1 0 1 1 1 0. Right? Actually, yeah. What is the value of this number? It's represented in 2's complement using 6-bit. Okay. What is the value in decimal of this number? Who can tell me? Step by step. You don't have to tell me the last value. Just tell me what to do.
And the complement.
Yeah, the 1's complement is 0 1 1 1 and then 0 0, and then add a 1 to that. What do you get? 1 0 1 1 1 0. Okay, so my magnitude here is 13 plus what? Plus 16. So 16 plus 13 is 29. Yeah, so my magnitude here is 29 and my sign is negative. Okay.
Sir,
Yes.
why we add 1 here?
This is the definition of the 2's complement. It's the 1's
So-
complement plus 1. Okay.
Okay.
It's the definition of the 2's complement. Okay. It's to add a 1 to the 1's complement. Okay. All right. So again, we use a terminology or a vocabulary. Okay. The 2's complement of a number is different from saying 2's complement representation. Okay. The 2's complement of a number is, for example, the 2's complement of A equals negative A. Okay. The 2's complement of A is negative A. Okay. So when I say to you the 2's complement of A, you just need to find its negative counterpart. Okay. So let's say that you have a 6-bit, for example, you have a 6-bit 2's complement representation. We would like to find the 2's complement of this number. So this number, we know it's positive. Okay. So we would like to find its negative counterpart. Okay. The 2's complement of this number means finding its negative counterpart. Okay. Again, the 2's complement, okay, is going to be 1's complement plus 1. Okay. So minus A is going to be A complement plus 1. Okay. So all I have to do is to complement the bits and then add 1 to them. So what is that going to be? It's going to be 1 0 0 1 0 0 plus 1 1 0 1 0 0 1. Okay, so this is my negative A. So negative 0 1 1 0 1 1 is equal to 1 0 0 1 0 1 in binary. Okay, this is in 2's complement representation. Okay, yeah. Any question? There is another way to do that. There is a shortcut to do it. Okay, in which you can, instead of finding, I mean, there is a shortcut because the methodology here involves finding the complement of the number and then adding 1. Maybe this is somewhat time consuming. So the shortcut is just 1 step. Okay, instead of doing it in 2 steps, okay, and then adding, you can do it in 1 step by just examining the number and then complementing some part of the number. Okay, so for here you will keep the 1 as is and then complement the rest of the number. You can see that this one is kept as is and the rest of the number is complemented. You can see here clearly. So this is 0 1 1 0 1 is converted to 1 0 0 1 0. Okay, so how does this work? We basically scan the number from right to left and find the first one and then leave everything to the right of this one, including itself as is, and then complement the remaining bits. Okay, let's take an example that illustrates this. So if you want to find the 2's complement of 1 0 1 0 0 0, okay, this is a 6-bit 2's complement representation. What is the so if this is A, for example, what is negative A? First of all, let's do it using the normal way, finding the 1's complement first. So finding the 1's complement, it's going to be 0 1 0 1 1 1, and then adding 1 to that, you get what? 0 with a carry of 1, 0 with a carry of 1, and then 0 with a carry of 1, and then 1 0 1 1 0. Okay. Did I get it right here? Anyone can check, please. 0 with a carry of 1, then 0 with a carry of 1.
Yes.
Carry 1 and 1 and 1. Okay, yeah, I got it right. Right, so this is the negative counterpart of the number. So minus A is equal to 0 1 1 0 0 0. First of all, sanity check. The sign bit must be different between the two numbers. Is this true? Yes, check. Okay, because A has a sign bit of 1 and negative A has a sign bit of 0. So negative A is positive and A is negative. Okay. The second thing, what is the value of this number here? It's going to be 8 plus 16, which is 24 plus 24. This is what? Negative A. So A must be minus 24. Okay. So now we turn to the shortcut. Instead of doing it in 2 steps, okay, and then finding the sum, we can do it right away. So I can say, well, if this is my A, and I would like to find the 2's complement of A, I scan A from right to left, from here, 0 0 0, and then I find the first one, okay, and then keep all this as is, okay, including the 1, and then complement the rest, okay, complement the rest of the numbers, okay. So my negative A is going to be 0 1 and then 1 0 0 0. Compare this with this. They are the same, right? So this is a shortcut that you can use, or you can keep using this method. Okay, yeah, actually they are not very different. Okay, but this one saves you a little bit of time. Okay, but do not use it unless you are convinced that it works. Okay. So what is the one of the advantages of the 2's complement is that it has a unique representation of the 0. The 0 is only all zeros number. Okay, all zeros is going to be the 0. Okay, so this is the super advantage of using the 2's complement. Also, another advantage is that you can do addition and subtraction using the same circuit with only minor modification. Okay, for example, if you want to do subtraction, A minus B, okay, you can write this as A plus minus B, and by definition negative B, okay, is the 2's complement of B, right, which is A and then plus B complement and then plus 1, right? What is this? Where did I get this from? I got it from here. Negative a into its complement is a complement plus 1. So negative b is b complement plus 1. Okay? All right? So I converted subtraction to addition here. Okay? With the complement, of course. All right? So I know that I can use my ripple carry adder. Okay, I'm going to elaborate on this in the next lecture, but right now, just for the sake of illustration, this is my A and this is my B, okay? And this is a 4-bit ripple carry adder, for example, RCA. And this is my carry N, all right? So if I input A here, if I want to get at the output A minus B, then I should input A here. And for here, I should input what? Instead of B, I input B complement, okay? And for the carry N, I input what? 1. So this circuit here produces A minus B. I know that. This is a property of the 2's complement, okay? And if I want, for example, a simple addition, so if I want A plus B, on the other hand, what I need to do is to input, instead of B complement, B, and instead of 0, instead of 1 here, I put a 0 here. So all I need to do is to control what I input, whether it's B or B complement, and whether my carry is going to be a 0 or a 1, and then I got an adder and subtractor of the same circuit. Okay, we will see how to do that in the next lecture, inshallah. Okay, but for now, I want you to understand how to do addition and subtraction using 2's complement. Okay, so addition and subtraction are very similar. Okay, in fact, they're both addition. There is no subtraction in 2's complement because we always convert addition problems or subtraction problems to addition problems. Okay, using the 2's complement. Okay, but we must, because our range is limited. Okay, we must watch for overflow. Okay, we must watch for overflow, and overflow occurs when the result is outside the range. For example, if we use 4-bit, and we add plus, let's say, plus 7 and plus 7, what is the result? Going to be plus 14, right? What is plus 7 in 2's complement? 4-bit, and then 0, 1, 1, 1. And then if you add this up, you get a 0 with a carry of 1, and then a 1 with a carry of 0, a 1 with a carry of 1, I'm sorry, and then a 1 with a carry of 1, and then a 1, right? The answer is correct if you interpret it as unsigned addition. But since we are doing signed addition here, okay, we must consider this bit as my signed bit, okay, which is bit number 4. I'm adding 2 positive numbers and I got a negative number here. So it must mean that I have an overflow. Okay, this is what it means to have an overflow. You add 2 positive numbers and you get a negative number, or you add 2 negative numbers and you get a positive number. Okay, so let's take an example here. We have a 5-bit 2's complement representation, and I'm adding these 2 numbers. Okay, the beauty of 2's complement addition and subtraction is that you do both like addition. Okay? Even if the other number is negative, okay, it will work out. Okay, it will work out somehow. Okay, so you just add them together and then magically you will get the correct result. Okay, so this problem here, although it is represented as addition, but you must understand that this is in fact subtraction. So I'm having a positive number and a negative number here. So effectively what I'm doing is subtracting this negative number, subtracting the magnitude of this negative number from this positive number. Okay, but in 2's complement we don't care. Okay, addition is addition, that's it. Okay, so all we have to do is to do the addition as if the numbers were unsigned. Okay, so this is going to give me 1, okay, and then 0, and then 0 with a carry of 1, and then 1 with a carry of 1, and then 0 with a final carry of 1. But since our number of bits is fixed and the width is fixed, I must discard this final carry. It's not part of my number. Okay, so I discard this final carry because it's not part of my number. My number is 5-bit, right? Now let's do a sanity check in order to see whether the result is correct or not. What is the value of this number? Help me. In decimal, I mean. What is the value in decimal?
13.
Plus 13, okay? Don't forget the plus because it is a signed number. What about this one? You must find the negative counterpart first and then put a negative sign in front of the converted number. So the negative counterpart here is going to be using the shortcut. It's going to be 001 and then 00, right? So I'm just scanning here, scanning to find the first one. So all of this will remain the same. And then I'll flip the remaining bits, okay? So this number here is 4. So, but my original number is negative, so I have a -4 here. Okay? And this number here is +9, right? Does this add up?
Yes.
Yeah, so 13 minus 4 is indeed +9. Okay? All right, we'll pick up from here next time, inshallah, giving more examples and then move on to the hardware implementation of the adder subtractor. But I want one favor from you, please. During the weekend, I want you to go over the lecture, this lecture specifically, okay? Because the next lecture will rely too much on the information that we presented in this lecture. If you just forget the information, okay, it will be, the next lecture will be too confusing for you, okay? So please review and help me deliver the information correctly to you, okay? Let me stop recording, unless you guys have a question, okay? You have a question and you want me to record it, maybe. Okay, guys, you should use, okay, I have seen some of you have participated in the chat area. Let me stop recording first and say it.